Hey AP Calc, this is the third video for our session on the shortcut rules of derivatives. So we're just starting to do the trigonometric functions, and we'll start with sine and cosine for now. So believe it or not, when you take the derivative of sine, the answer is cosine. So the cosine graph is actually the graph or the formula that gives you the slope for sine of x at any given x. It's an amazing thing that happens. So basically, cosine x is the slope graph of sine x. And likewise, if you take the derivative of cosine x, the slope can be graphed using negative sine x. It's an amazing relationship that these two have. So, when we take the derivative here, this is just constant multiple rule. So, y prime is going to be 2 times the derivative of sine. The derivative of sine is cosine x, and boom, we're done. B, let's rewrite this as negative 1/2 sine x minus 1/2 sine x. When I rewrite this, I realize, you know what, this isn't really a hard problem at all, because negative 1/2 minus 1/2 is negative 1. I actually have negative sine x here, negative 1 sine x is here, right? So when I take the derivative, I'm going to get negative 1 times the derivative of sine is cosine x. So my derivative is negative cosine x. Now you could have done this and gotten negative 1/2 cosine x minus 1/2 cosine x, and then you would still end up with negative cosine x. So that works either way. You can combine like terms before or after you take a derivative. For s of x here, we're going to do the sum rule. So the derivative of x is 1. Remember, this is going to be x to the first, so 1 x to the 1 minus 0, or 1 minus 1 is 0. And this is just 1, so that's why that drops out, and we just get the coefficient of the x as our derivative. So 1 cosine x has the derivative of negative sine, so I'm going to say plus negative sine x, or I could have just said minus x. So I'm going to get 1 minus sine x is my derivative. Okay, let's go ahead and flip to the next page. The next page on your note sheet is about rates of changes. Rates of changes are important, and they're related to the derivative, because if you remember, derivative is the slope of the tangent line. So what does that have to do with the rates of change? Well, rate of change is a fraction that has a different unit for the numerator and denominator, like miles per hour, or miles per gallon, or item per dollar, or whatever you want to write. There's a lot of different rates that we use. Dollar per hour if you're getting paid for a job. So each of these rates can be seen as slopes of the graph. Well, what do you mean, Mr. Rigger? Well, what if I have hours here and I have miles here? This is a distance versus time graph. And if I have this point, x1, y1, and I have this point, x2, y2, my slope is going to be y2 minus y1 over x2 minus x1. But y's are in miles, and the x's are in hours. So my slope here is a speed, miles per hour. So when we have rates, really we can think of them as slopes of graphs. This whole idea is the change in this over the change in this. So let's put this in practice. when we're talking about physics and the height of a object in motion that's been thrown using gravity to think about when it will come back and hit the ground, we get this function. The height position, or the position of the thing is -1/2 times the speed of gravity, the acceleration due to gravity, I mean, times t squared plus the initial velocity at which you throw it, times t plus s of 0, the initial height. So this is the acceleration due to gravity. And there are two different units we use for this. Either it's -32 feet per second squared, or it's -9.8 meters per second squared. Which means when we take half of that, we're going to be looking at -16 or -4.9. V sub 0 is the initial velocity, how fast it started at time t0. And this is the initial position, or the initial height. So, a ball is being dropped from a height of 100 feet. So I just learned from that S0 is 100. What is its initial velocity? Well, it's being dropped. So it's not being thrown, so the initial velocity is not 100, it's 0. What function can be used to model the position of the ball as it relates to time? Well, I have this s of t right here that I'm going to use. The position is going to be -1/2. Now, we're going to use the feet one, so times 32 feet per second squared. We don't usually put the units in here. Plus 0, oops, I missed my t squared here, plus 0 times t plus my 100, my s of 0. So, I don't usually put my units, so I'll scribble them off. Now, notice I have 1/2 g, -1/2 g. Really, the idea is if you're using g as a negative, this is going to be a positive. And if you're thinking about g as positive, then you're going to have that as a negative. Since acceleration due to gravity is actually negative, it pulls you back down to the ground, this is really just 1/2 g times t squared. And that's a little typo on the note sheet. So, we're going to continue going with this. This is really, to clean it up, -16 t squared plus 0t, we're not going to write that, plus 100. That's s of t. Now, if I want the average velocity is just going to be when I take my position final minus my position initial, and I do this over time final minus time initial. This is really just slope. But it's slope of the secant line. That's how I find an average. If I want the instant slope, instantaneous, velocity is going to be s prime of t. So the instantaneous velocity is the slope of the tangent line. That should be enough to get you through this lesson.